So we are doing Newton's laws and primarily been really focusing on Newton's second law problem solving. And we are going to add in more details about friction and rotational motion, uniform circular motion problems, but still just using Newton's second law. But I'd like to take a little hiatus and talk about Newton's third law. So let's just remind ourselves, Newton's laws, the law of inertia is the first law, F equals ma is the second law, which is really, more than anything, it's Newton's first law in equation form. Newton's third law is additional information. For every action, there's an equal and opposite reaction. Remember, we had discussed the fact that action and reaction are not really meaningful in a physics sense to us. But what Newton really means is for every force, there's an equal and opposite force. We'd also discussed that that really is not good enough either, because what do we mean for every force is an equal and opposite force? For every force, we can always find another equal force in the opposite direction. But what Newton is saying here is that there are two particular forces that always must always be equal and opposite. And really, in order to understand Newton's third law, we have to state it in a slightly more specific way. Before I say that, we did talk about the concept of force pairs. So the kinds of forces that Newton is talking about in the third law is a force pair. And a force pair is something in particular. So to understand Newton's third law, it really is this. If object A exerts a force on object B, then object B must exert an equal and opposite force back on A. Now you might say, well, okay, sure, that sounds reasonable, but actually we'll see a lot of situations where you're a little bit surprised. So what I mean, for example, is if I have two boxes and they can be different masses and we are pushing on the two boxes, there are forces between the two boxes, 1 and 2. Because boxes 1 and 2 are in contact with each other, there are normal forces on those boxes, and box 1 exerts a force on box 2. So box 1 exerts a force on box 2, F1 on 2, and therefore box 2 must exert a force back on box 1. So this is box 1, and this is F2 on 1. Because they're in contact with each other, if one exerts a force on the other must exert a force back. But the thing that Newton's third law tells us is that this is a force pair where those two are equal. Doesn't matter what the masses of the boxes are, doesn't matter how hard I'm pushing, those two forces are always equal. That's what Newton's third law tells us. Those two are a force pair. So some things may seem obvious, right? If I put a box on the floor, or it doesn't have to be a box, let's say that you're standing on the floor. This is you, and you have a weight of not 150 newtons, that would be 150 pounds. Let's just make it 500 newtons. You have a weight of 500 newtons. Then you exert a force on the floor. What's the force that you exert on the floor? The normal force, because you are touching the floor. It is 500 newtons, right? So the force of you on floor is equal to 500 newtons. Now, there's an additional thing to bring in here, which is that why is the force of you on the floor equal to 500 newtons? And it is in the downward direction. Why is that force 500 newtons? You might say, because my weight's 500 newtons. But no, that's not true. It's because your weight it is partly because your weight is 500 newtons, but it is because you are not accelerating. If you were pushing on the floor, like getting ready to jump, and you're accelerating, then the force you're exerting on the floor is bigger than 500 newtons in order to push yourself off the floor. Or if this was an elevator, moving downward, accelerating downwards out from under you, then while your weight is 500 newtons, you're not necessarily exerting a force on the floor of 500 newtons. The only reason why you're exerting a force on the floor of 500 newtons is because you're in equilibrium. And the reason why we know that is, let's draw a free body diagram of U. Let's just assume a boxical U, a box-shaped U, and let's look at the forces on you. right? So the forces on you are the gravitational force, which is 500 newtons. That's what weight is. And the normal force of the floor on you, not of you on the floor. And we see that because A is equal to 0, therefore, if we apply F net equals ma, and we do this properly and we choose a positive direction, I don't know, let's choose up as the positive direction, we get therefore Fn minus mg is equal to 0 because acceleration is 0. So therefore, the normal force on you is equal to mg. That comes from Newton's second law, not Newton's third law. The normal force on you is mg. But because the normal force on you is mg, because of Newton's third law, so let's say what this means. Before I talk about Newton's third law, what this means is that the force of the floor on you is equal to 500 newtons, and that's in the upward direction only because that's what we drew in our force diagram, and that's what we got, 500 newtons up. So therefore, by Newton's third law, because the force of the floor on you is 500 newtons up, the force of you on the floor is 500 newtons down. This is the force of A on B is 500 newtons up. Therefore, the force of B on A is 500 newtons down. That's how I know the force on the floor is 500 newtons. It's not because my weight is 500 newtons. And we'll do an example in an elevator to show that's not necessarily true, right? So we'll do that example coming up soon.